Start with a line segment of length 1. Cut out the middle third of the segment, then the middle thirds of each of the two remaining segments, and so on. Continue this process to infinity. The resulting set of points is called the Cantor set, named after Garrick Cantor. The most baffling property of the Cantor set is that, on one hand, its length is 0, but on the other hand, there are as many points in the Cantor set as on the entire real number line. Firstly, the Cantor set's length is 0, as it is multiplied by 2/3 after each step, and doing so infinitely produces a length of 2/3 to the infinite power, or 0. Now for the less intuitive part. The Cantor set has the same number of points as the real number line. But how does this work? Well, two sets have the same number of elements when there is a one-to-one correspondence between the two sets. For example, we can correspond the set of all real numbers with the set of real numbers from 0 to 1. Now, we want to build a one-to-one correspondence between the Cantor set and the initial segment, and therefore with the entire real number line. But is this even possible? We can rewrite each number on the line segment with a ternary decimal. Since we repeatedly cut out the middle third of the line segment to form the Cantor set, each decimal in the Cantor set lacks the middle digit of the ternary system, which is 1. So the ternary decimal 0.022 is in the Cantor set, but 0.012 is not because it contains a 1 in its ternary decimal representation. In fact, each decimal that contains only 2's and 0's is in the Cantor set. Now, consider the initial line segment. Each point on the initial line segment can be rewritten in binary form, with only two digits, 0 and 1, after the decimal point. But now we can simply replace all the 1's from the binary decimals in the line segment with 2's, obtaining the Cantor set. That's our one-to-one correspondence, and that's why the number of points in the Cantor set is as infinite as the entire real number line, even though its length is 0.